You know, when you're coding, there are always a ton of ways to solve the exact same problem. But have you ever stopped to think what actually makes one solution better than another? It's not as simple as you'd think. Today, we're going to go on a quest to find a universal, rock solid way to measure code and figure out which approach is truly the most efficient.
Okay, so let's just dive right in. We're going to kick things off with a question that seems super simple on the surface, but it's something every single developer has to wrestle with.
So, I want you to think of this like a detective story, right? We've got two suspects, or two chunks of code. They both get the job done, they both solve the crime. Our mission is to figure out, with cold, hard evidence, which one is the superior detective. So let's look at a classic example. We need to find something in a list. Code A on the left is the straightforward brute force method. Just look at every single item one by one until you find it. Code B is a bit more clever. It keeps splitting the list in half and narrowing down the search. Both work, but our whole quest here is to find a bulletproof way to prove which one is actually better. Now, before we get to the right answer, it's actually super helpful to look at a couple of traps, a few common sense ideas that seem really good at first, but they end up leading us completely down the wrong path. So, what's the first thing you'd probably think of? I mean, it's obvious, right? Just run both of them and time it. Pull out a stopwatch, see which one finishes first. The faster one wins. Simple. But is it, really? And boom, here's the problem. The time you get is totally tied to your specific computer. If you run the code on a crazy new gaming rig, it's going to be blazing fast. Run that exact same code on a 10-year-old laptop, and the results will be totally different. A stopwatch isn't measuring the code's quality, it's measuring the code on a very specific piece of hardware. It's just not a universal metric. Okay, fine, the stopwatch is out. So what's plan B? Well, maybe we just count the lines of code. It kind of makes sense, right? Shorter code feels cleaner, more elegant. You'd think fewer lines means less work for the computer. But yeah, that falls apart pretty quick too. The number of lines has everything to do with the programming language you're using, or even just the personal style of the programmer. You could write something in a single, powerful line of Python that might take 10 lines to write in another language. So line count, also totally unreliable. So it's pretty clear what we need. We need a standard, a universal measure that doesn't care about your computer or what language you wrote it in. The only thing that should matter is how the amount of work changes as the size of the problem, let's just call that size n, gets bigger and bigger. And that right there leads us to the big aha moment. This is the breakthrough concept that finally lets us compare apples to apples. We have to stop thinking about raw seconds and start focusing on something much, much more interesting. And that something is the rate of growth. It sounds a little academic, but the idea is simple. We don't really care if a program takes zero point zero 0.01 seconds or zero point zero 0.02 seconds for a small list. What we really care about is what happens to that runtime when the list has 1,000,000 items or 1 billion. It's all about how the workload scales. Okay, here's a great way to think about it. Let's say you go out and buy a $50,000 car and a $200 bicycle on the same day. When your friend asks what you bought, what do you say? You say, I bought a car. The cost of the bicycle is so small in comparison, it's basically a rounding error. It's insignificant. We're about to do the exact same thing with our code. And this table right here shows you the math behind that car analogy. Let's say an algorithm takes n squared plus 100n plus 102 steps to run. When n is tiny, like 1, all the parts kind of matter. But just look at what happens as n gets huge. The n squared part, that's our car, it just completely takes over. It grows so ridiculously fast that the other parts become totally insignificant. That one dominant term is the only thing we need to pay attention to. And this chart really drives the point home. You can see just how different these growth rates are. An algorithm that grows linearly, or O of n, scales pretty predictably. But a quadratic one, O of n squared, that curve just shoots for the moon. It gets slow, fast. This is why picking an algorithm with a lower rate of growth is absolutely critical if you want your code to perform well at a massive scale. Okay, so we get it. We need to focus on the dominant part, the rate of growth. Now let's learn the official language, the lingo that computer scientists all over the world use to talk about this. It's called Big O notation. And, okay, deep breath. I know this formal definition looks terrifying. It's pure math, talking about constants and variables. But please, don't worry about memorizing this, because the core idea behind all that scary-looking math is actually incredibly simple.
This is it. This is all you really need to know. That's what all that math boils down to. Big O doesn't tell you the exact runtime, it tells you the category of its growth. It basically puts a ceiling on it, guaranteeing that your program will never, ever grow faster than this specific rate. Here's a perfect way to think about it. Big O is the worst case scenario. It's your guaranteed maximum wait time. Like when a delivery service says your package will arrive in, at most, 3 days. It might show up tomorrow, which is great, but you have a guarantee it won't take longer than 3 days. Big O is that exact same performance guarantee for our code. So why do we care so much about this worst-case guarantee? Well, because when you're building software for the real world, you have to plan for the worst day, not the best one. This kind of analysis is what makes sure your e-commerce site doesn't melt down on Black Friday, or your social media app doesn't just crash when a post goes viral. It's all about building things that are reliable and robust no matter what you throw at them. So let's bring it full circle. Remember our function, n squared plus 100n plus 102? With Big O notation, we do exactly what we did with the car and the bicycle. We look for the most dominant term, the n squared, and we drop everything else. So we can just say the complexity is O of n squared or Big O of n squared. Simple as that. Okay, that was a lot. So let's just quickly recap our whole journey, from that simple starting question to this really powerful way of thinking. So our quest started with that simple question: how do you find better code? We quickly figured out that the obvious answers, like stopwatches and line counts, just don't work because they aren't universal. The real breakthrough came when we shifted our focus from raw speed to how the performance scales. And that led us to our ultimate tool, Big O notation, the universal language for describing that scaling behavior. So if you remember anything, remember these 3 ideas. The whole process is called running time analysis. The thing we're actually measuring is the rate of growth. And the special language we use to talk about that worst case growth is Big O notation. And all of this leaves us with one last big thought. Understanding Big O isn't just some boring academic exercise. This is the fundamental tool that engineers at places like Google, Netflix, and Amazon use every single day to build systems that serve billions of people. An ON squared algorithm might be perfectly fine for 100 users, but it will absolutely fall over and die with 1 billion. So the real question this leaves us with is, how do we get even smarter? How do we design solutions with even better growth rates to build the technology that will power our future?